Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at finding eigenvalues of a matrix. So in this topic we will see various techniques for finding eigenvalues. First 2 by 2, then 3 by 3 matrices. We're then going to look at some examples, and then we'll introduce the QR decomposition, which is used to find the eigenvalues of larger matrices. So in this topic, we're going to discuss algorithms for finding the eigenvalues of a matrix. We'll start with 2 by 2 matrices, we'll investigate 3 by 3 matrices, and then we'll look at the general case of finding eigenvalues for n by n matrices. So to find the eigenvalues of a 2 by 2 matrix, real or complex, we simply calculate the determinant of lambda times the identity minus the matrix, which is the determinant of what you see there. And that's just the product of the diagonals minus the product of the off diagonals. We can expand the first term. Now, taking a look at that, you'll notice that a11 plus a22 is just the trace. So we have lambda squared minus the trace of a times lambda. The last term is, wait a second, that's the determinant. And again, you should expect the constant term to be the determinant, for if lambda is equal to 0, we are just calculating essentially the determinant of negative a. Consequently, using the quadratic formula, we get that the two eigenvalues are found using this formula. However, bringing the 2 into the square root, we get a slightly easier to remember formula. So essentially we have trace over 2 plus or minus the square root of trace over 2 squared minus the determinant, which is a little bit easier to remember as follows. Trace over 2 plus or minus trace square root of trace over 2 squared minus determinant. For example, consider this 2 by 2 matrix. The trace is 10, and therefore the trace over 2 is 5. The determinant is 1. Therefore, the two eigenvalues are 5 plus or minus square root of 5 squared minus 1, and that just simplifies to 5 plus or minus 2 root 6. Next, consider this 2 by 2 matrix. The trace is negative 2.9 plus 0.7, which is negative 2.2. Therefore, the trace over 2 is negative 1.1. The determinant is 4.45, and you can calculate that yourself. Therefore, the eigenvalues are negative 1.1 plus or minus the square root of negative 1.1 all squared, which is 1.21, minus the determinant. That's just negative 1.1 plus or minus root negative 3.24, so clearly they are imaginary or complex eigenvalues. And that's just negative 1.1 plus or minus 1.8j. All right, now to find the eigenvalues of a 3 by 3 matrix, we simply have to find those values of lambda such that lambda times the 3 by 3 identity minus a is non-invertible. That is, the determinant of that is 0. All right, now to calculate the determinant of a 3 by 3 matrix, you'll recall we write down the matrix twice. We then proceed to multiply the entries of this first diagonal, and that is the first step. We proceed with the next two, and we multiply them together. So this now has us subtracting off those two products of entries. We then multiply these together and subtract that from our results so far. Multiply these three together, subtract, and multiply these three together and subtract. All right, so that is our determinant. And therefore, the roots of this cubic are the eigenvalues of the 3 by 3 matrix. Now, unless you can easily detect an eigenvalue, you must end up solving a cubic, which means generally using software. Now, if the matrix A is not invertible, you are therefore guaranteed that 0 is an eigenvalue, so 0 must be a root. Well, in that case, the characteristic polynomial may look something like this, where C1 is non-zero. Well, in this case, we can factor out a lambda, which means what's left is a quadratic. Therefore, the three roots would be 0 and this expression on the right. And from a few slides ago, this should look familiar. So it's just basically negative C2 over 2 plus or minus the root of C2 over 2 all squared minus C1. So those would be our three eigenvalues. On the other hand, if C1 is also equal to 0, that means we have two 0 eigenvalues, and consequently the third eigenvalue is just negative C2, whatever that coefficient worked out to be. The last case is that we simply have the characteristic polynomial lambda cubed equals 0, which means that all three roots are 0 and therefore all three eigenvalues are 0. This does not mean that A was the 0 matrix. There are non-zero matrices that have three eigenvalues equal to 0. Now, if we're calculating the eigenvalues of a real matrix that is invertible, well, this is the characteristic polynomial, but all the coefficients are real. Therefore, by the fundamental theorem of algebra, at least one of the three roots must be real. If you can detect one of those roots, or you can find it using Newton's method, you can then factor that root out using polynomial long division. So essentially, you'd perform this calculation and you'd find the quotient, with the remainder, of course, being 0, as lambda 1 is one of the roots. Consequently, the three eigenvalues would be the one you found and the expression on the right. Now consider, for example, this matrix. As you can see, it is a symmetric matrix, therefore we are guaranteed all of the eigenvalues are real. However, in addition to this, you'll notice that the third column is the sum of the first two columns, and therefore the matrix must be singular since the columns are not linearly independent. The characteristic polynomial, were you to calculate it, would be this expression here, and you'll notice we can factor out a lambda. Therefore, lambda 1 is equal to 0 is one of the roots and therefore an eigenvalue. Once we factor out lambda, we're left with this quadratic, and the roots of that quadratic may be found with the quadratic formula. So we have 14 plus or minus square root of 14 squared, 196, minus 4 times 48 all over 2. Well, this is just 7 plus or minus root 4 over 2, which is just 7 plus or minus 1. Therefore, the eigenvalues of this matrix are 0, 6, and 8. And because it's a symmetric matrix, the eigenvectors corresponding to these three eigenvalues must be orthogonal. All right, Consider, for example, this invertible matrix. The characteristic polynomial of this matrix can be found to be this cubic polynomial. Now, we observe that negative 13 minus 27 is negative 40, whereas 1 plus 39 is also equal to 40. Therefore, lambda equals 1 is a root and therefore an eigenvalue. Let's use long division to factor out that root. So here we're going to do polynomial long division, dividing out the linear monic polynomial lambda minus 1. So to do this, we observe that we must, to get rid of the lambda cubed, we must multiply lambda minus 1 by lambda squared. All right, so we multiply it out and we subtract that off. Negative 13 lambda squared minus negative lambda squared is negative 12 lambda squared. Bring down the plus 39 lambda. To get rid of the negative 12 lambda squared, we must subtract from that negative 12 times lambda minus 1. So negative 12 times lambda minus 1 is that expression there. We subtract the 2, and that leaves us with 27 lambda. We bring down the 27. So now to eliminate that, we must subtract off 27 times lambda minus 1, and thus we subtract off that polynomial, and of course when we subtract that off, we get 0. Why is it 0? Because you will recall that that is the value of the polynomial at lambda when evaluated at lambda equals 1, which is 0. It is a root. All right, now the roots of what remains, lambda squared minus 12 lambda plus 27, can simply be found with the quadratic formula. So we have 12 plus or minus root of 144 minus 4 times 27 all over 2, and that's just 6 plus or minus root 36 all over 2, or over 2, and that is just 6 over 2, or 6 plus or minus 3. Therefore, the eigenvalues of this 3 by 3 matrix are 1, 3, and 9. Again, this is really only possible if you can quickly detect one of the roots of the characteristic polynomial. Now, to find the eigenvalues of a larger matrix, the techniques are essentially based on this routine or algorithm. If we want to find the eigenvalues of a matrix A, we initialize A naught with that matrix. Now, we haven't covered a QR decomposition. However, a QR decomposition decomposes a matrix into an isometric, or for real matrices, an orthogonal matrix Q, and an upper triangular or right triangular matrix R, essentially saying that all the entries to the right of the diagonal are non-zero. All right, so given A naught, we calculate the QR decomposition. However, we now have Q naught and R naught. We assign A1 the product R naught Q naught, so we reverse the matrices. And because in general matrix multiplication is not commutative, A1 is not equal to A naught. We actually repeat this many times. So with A sub k, we calculate the QR decomposition Q sub k, R sub k. Then the next A sub k plus 1 is assigned R sub k times Q sub k. The diagonal entries of Q sub k, R sub k converge to the eigenvalues. All right, for example, consider the following 4x4 matrix. This has 4 eigenvalues, and it happens that the eigenvalues are such that 2 of them are real and 2 appear as a complex conjugate pair. Now, I just ran this algorithm 37 times, and you will notice that the product Q37R37 looks like this, and everything below the diagonal is quite small. All right, let's get rid of those, and we see that this is essentially an upper triangular matrix, but not quite. Notice that one eigenvalue is there. The last eigenvalue is at that location. But what's left is a 2x2 matrix here in the center. Now, this 2x2 matrix happens to have 2 eigenvalues, specifically a complex conjugate pair of eigenvalues. So, using the formula we saw previously, we can calculate the eigenvalues of this 2x2 matrix, and we get that those 2 eigenvalues are the last 2 eigenvalues of the matrix A. So essentially what we have here is a block upper triangular matrix where the entries along the diagonal are either 1x1 entries, which are real eigenvalues, at least if we start with a real matrix, or a 2x2 block, where the eigenvalues of that 2x2 block are a complex conjugate pair of eigenvalues. All right, but please remember, this is beyond the scope of the course. This is only being taught so that you are aware how such algorithms work, as well as introducing the QR decomposition. Following this topic, you now know how to find the eigenvalues of a 2x2 or a 3x3 matrix. And even with a 3x3 matrix, it may not be that easy. You also understand that there are algorithms for finding eigenvalues of larger matrices. And you have had a brief introduction to the QR decomposition, which is used in finding these eigenvalues for larger matrices. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!